What if everything we know about the universe, every law of physics, every cosmic rule we take for granted, is just the surface of something far stranger? Picture this: invisible forces tugging at the fabric of reality, unseen dimensions curled up like hidden folds in space, and mysteries so profound they rewrite the very definition of existence. These aren't ideas from science fiction. They're real theories born from the brightest minds in physics, each one a puzzle piece in the grand enigma of our cosmos. And today, we're diving deep into 30 of the most mind-bending, reality-shaking ideas about the hidden forces that might actually govern everything around us. Think about the last time you stared up at the night sky, feeling that humbling mix of awe and wonder. Those distant stars, those swirling galaxies, they're all dancing to a tune we can't quite hear, orchestrated by forces we're only beginning to glimpse. Dark energy, dark matter, quantum entanglement, these aren't just buzzwords. They're clues hinting at a universe far weirder and more beautiful than we ever imagined. Some of these theories suggest entire dimensions exist right beside us, just out of reach. Others propose that time itself might be an illusion, or that the cosmos is a hologram, a projection of deeper, unseen laws. This isn't just about abstract science. It's about the thrill of discovery, the joy of peeling back the layers of reality to ask, what's really out there? Whether you're a casual stargazer or someone who devours every space documentary, these ideas will stretch your mind in ways you didn't think possible. So buckle up, we're about to explore 30 theories that challenge everything we thought we knew, from the bizarre to the breathtaking, the unsettling to the utterly sublime. By the end, you might never look at the universe the same way again. Imagine a cosmic glue, invisible and silent, weaving through the vast emptiness of space, holding the universe together. That's dark matter, an enigmatic substance that makes up roughly 27% of everything in existence, yet we've never seen it, touched it, or even directly detected it. So how do we know it's there? The answer lies in the way galaxies move. Stars on the outer edges of spiral galaxies rotate so fast that, according to the rules of gravity we understand, they should have been flung into the void long ago. But they're not. Something unseen, something with tremendous gravitational pull is keeping them tethered. That something is dark matter. Think of it like this: if the universe were a grand puppet show, dark matter would be the hidden strings. We don't see the strings, but we can see their effects: the way galaxies cluster together, the way light bends around massive cosmic structures, even the way the universe itself expanded after the Big Bang. Without dark matter's gravitational scaffolding, none of it would hold its shape. Yet, for all its influence, it refuses to interact with light or any known form of matter. It doesn't absorb, reflect, or emit anything we can measure, leaving scientists to chase shadows in the dark. So what could it be? Theories range from exotic particles that barely interact with normal matter to entire hidden dimensions leaking gravity into our own. Some experiments hunt for faint flashes of light when these ghostly particles collide with rare materials deep underground. Others scan the skies for distortions in starlight, hoping to map the invisible web of dark matter stretching across the cosmos. But so far, it remains the universe's most stubborn secret, a reminder that, for all our knowledge, we've barely scratched the surface of reality's deepest mysteries. If dark matter is the invisible glue holding galaxies together, dark energy is the mysterious force ripping the cosmos apart at the seams. Picture the universe as a balloon inflating at an ever-increasing speed, not because someone's blowing harder into it, but because the rubber itself is stretching faster with each passing moment. That's the eerie reality of dark energy, an enigmatic force making up a staggering 68% of the universe's total energy, yet we know almost nothing about what it truly is. Back in the late 1990s, astronomers made a discovery that turned cosmology upside down. They expected the universe's expansion, set in motion by the Big Bang, to be slowing down due to gravity's relentless pull. Instead, they found the opposite. The expansion was speeding up, as if some invisible hand was pressing harder on the cosmic gas pedal. This wasn't just surprising, it shattered decades of assumptions. Imagine throwing a ball into the air, only to watch it shoot upward faster instead of falling back down. That's the level of cosmic defiance we're dealing with. So what's behind this acceleration? The leading theory points to something called the cosmological constant, an energy woven into the very fabric of space itself. Empty space, it turns out, might not be empty at all. Quantum physics suggests that even a perfect vacuum teems with fleeting particles popping in and out of existence, and this seething energy could be driving the universe apart. But here's the twist. When scientists calculate how much energy this quantum foam should contain, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the biggest mismatch between theory and observation in all of science. Alternative ideas abound. Some theorists propose that dark energy isn't constant at all, but a dynamic field that changes over time, like an invisible fifth force of nature. Others suggest our understanding of gravity itself might be flawed on cosmic scales, requiring a rewrite of Einstein's equations. Then there are the truly mind-bending possibilities, like our universe being just one bubble in an infinite multiverse, each with its own laws of physics, and dark energy is simply a side effect of our bubble's unique properties. Whatever the answer, the implications are staggering. If dark energy continues unchecked, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future civilizations with a sky devoid of stars. But if it weakens or reverses, the universe could collapse in a big crunch. Or perhaps it's just one chapter in a much stranger cosmic story we've yet to uncover. What's certain is this: dark energy isn't just a puzzle, it's a reminder that the universe still holds secrets capable of rewriting the rules we thought we knew. Here's the paradox of empty space. It's not empty at all. Even in the deepest vacuum, where every atom, every particle of light has been stripped away, the universe is still crackling with activity. This is the realm of quantum vacuum fluctuations, a bizarre phenomenon where particles spontaneously burst into existence, only to vanish again in the blink of an eye. It's as if the fabric of reality itself is fizzing with energy, a cosmic froth where something emerges from nothing over and over again. These fleeting particles aren't just theoretical quirks. They're a fundamental prediction of quantum mechanics, backed by startling evidence. In 1948, physicist Hendrik Casimir predicted that if you placed two uncharged metal plates incredibly close together in a vacuum, they'd be pushed toward each other by an invisible force. The reason: the tiny space between the plates limits the kinds of quantum fluctuations that can occur there, while outside, the particles continue popping in and out unfettered. The result: more pressure outside than inside, creating a measurable push. Decades later, experiments confirmed this exact effect, proving that empty space is anything but still. But the implications go far beyond a lab curiosity. Some theories suggest these fluctuations could be the engine behind cosmic expansion, the hidden driver of dark energy itself. Imagine the vacuum of space as a vast, seething ocean. Each particle-antiparticle pair that appears is like a tiny bubble surfacing for a split second before collapsing back into the depths. According to quantum physics, these bubbles carry energy, and if space itself is brimming with them, their combined effect could be enough to stretch the universe apart at an accelerating rate. There's just one problem. When physicists calculate how much energy these fluctuations should contribute, the numbers are astronomically off, suggesting either a gap in our understanding or that something even stranger is at play. Then there's the truly mind-bending possibility. These flickers of existence might not just shape our universe, they could birth entirely new ones. In certain interpretations of quantum theory, a fluctuation could, under the right conditions, trigger an inflationary expansion, creating a self-contained bubble of spacetime with its own laws of physics. Picture a foam of universes, each bubble born from the quantum chaos of another, sprouting endlessly in an unseen multiverse. It's a humbling thought. The spark that ignited our cosmos might have been just one ripple in an infinite sea of possibilities, a cosmic accident with no more significance than any other random fluctuation. Yet for all their mystery, these quantum whispers aren't entirely beyond our reach. Advanced detectors, like those hunting for gravitational waves, might one day pick up faint echoes of these fluctuations in the fabric of spacetime. Other experiments aim to manipulate vacuum energy directly, tapping into what some call the zero-point energy of the universe. Whether these efforts succeed or fail, one thing is certain: the quantum vacuum isn't just background noise. It's a frontier, one that challenges our deepest notions of reality, energy, and even the meaning of nothing itself. What if dark matter isn't the only explanation for the universe's hidden gravitational pull? Enter modified Newtonian dynamics, or MOND, a radical idea that turns the mystery on its head by suggesting there's no unseen matter at all. Instead, gravity itself might work differently than we thought, bending the rules in places where Newton and Einstein's equations seem to fail. Imagine the universe as a vast, intricate machine where the gears start slipping at the edges, not because parts are missing, but because the mechanism has a flaw we never noticed. That's the core of MOND, a tweak to the very laws we thought were set in stone. The theory was born from a stubborn inconsistency. When astronomers measured how stars orbit the centers of galaxies, they found something odd: the outer stars moved far faster than Newton's law of gravity predicted. The mainstream solution: dark matter, an invisible scaffold holding galaxies together. But in 1983, physicist Mordechai Milgrom proposed a different fix. Maybe gravity doesn't weaken as sharply over vast distances as we assumed. Instead, at extremely low accelerations like those felt by stars on the fringes of galaxies, gravity's pull levels off, becoming stronger than expected. It's not that extra mass is lurking unseen, it's that gravity itself has a hidden quirk. At first glance, MOND seems elegant. It explains galaxy rotation curves without invoking mysterious, undetectable particles. Certain dwarf galaxies, for example, fit MOND predictions beautifully, while dark matter models struggle to account for their structure. There's even evidence that some galactic collisions, like the Bullet Cluster, often hailed as proof of dark matter, might not fully rule out MOND alternatives. But here's the catch: MOND falters at larger scales. The cosmic web, the universe's filamentary structure, and the way galaxy clusters move all align tightly with dark matter's gravitational blueprint. Without some form of unseen mass, MOND struggles to replicate these patterns. Then there's the deeper question: if gravity behaves differently on cosmic scales, why? Relativity has passed every test thrown at it for over a century, from GPS satellites to black hole shadows. MOND, by contrast, lacks a unifying theory to explain its proposed modifications. Some versions try to bridge the gap by tweaking Einstein's equations, suggesting spacetime itself responds differently under faint tugs of gravity. Others speculate that MOND hints at undiscovered physics, like a hidden connection between gravity and the quantum realm. The debate isn't just academic, it cuts to the heart of how science confronts the unknown. Dark matter hunters point to experiments closing in on potential particles, while MOND advocates argue we're bending over backward to preserve old laws instead of revising them. And in a twist, some theories now explore hybrid models where both dark matter and modified gravity play a role. It's a cosmic tug of war between two visions of reality, each with its own triumphs and blind spots. One thing's certain: whether MOND ultimately holds up or not, it's forced physicists to question their assumptions. Sometimes the biggest breakthroughs come not from confirming what we know, but from daring to ask, what if we've had it wrong all along? At the heart of every atom, beneath the chaos of quantum particles and the vastness of cosmic forces, there might be a secret harmony, a symphony of unimaginably tiny strings vibrating in the hidden depths of reality. This is the vision of string theory, a breathtaking attempt to unite all the universe's forces under a single mathematical melody. Instead of particles as isolated dots, imagine them as microscopic loops of energy, each vibrating at a unique frequency like the strings of a violin. The pitch of these vibrations would determine whether a string manifests as an electron, a quark, or even a particle of light. It's an idea so elegant it could rewrite physics from the ground up. But there's a catch. These strings would be vanishingly small, around a billionth of a trillionth the size of an atom. To even begin detecting them, we'd need particle colliders the size of entire galaxies. So why do physicists cling to such an untestable idea? Because string theory promises something revolutionary, a theory of everything. In our current understanding, gravity and quantum mechanics speak entirely different languages. Gravity shapes the cosmos on grand scales, while quantum rules govern the subatomic realm, and the two refuse to reconcile. String theory offers a bridge. In this framework, gravity emerges naturally from the same vibrational patterns that create particles, weaving all forces into one cohesive tapestry. Then there's the twist that stretches the imagination. These strings don't dance in the 3 dimensions we know. They vibrate in 10 or even 11 dimensions, with the extra ones curled up so tightly we'd never notice them. Picture a garden hose seen from afar. It looks like a simple line, but up close you realize it's a cylinder. In string theory, our entire universe might be like that hose, with hidden dimensions folded into every point in space. Some versions of the theory suggest these extra dimensions could explain why gravity is so weak compared to other forces. It might be leaking into unseen realms, diluted across dimensions we can't access. Yet for all its beauty, string theory remains a castle in the clouds. Without experimental proof, it's been criticized as more philosophy than physics. The math is so complex that even slight tweaks can spawn entirely new versions of the theory. Some estimate there are 10 to the power of 500 possible configurations, each describing a different universe. This landscape of possibilities leads to a startling thought. Our universe's laws might not be fundamental. They could be accidental, one tune among countless others in a multiverse of cosmic symphonies. That doesn't mean scientists have given up. Some hunt for indirect clues, like faint imprints of extra dimensions in gravitational waves or relics from the Big Bang. Others explore black holes, where string theory predicts information isn't destroyed but encoded in vibrating strings on the event horizon. Even if the theory never finds direct confirmation, its mathematical innovations have already reshaped other fields, from quantum computing to our understanding of spacetime itself. So is string theory the final answer, or a magnificent dead end? For now, it remains a testament to human ambition, an attempt to hear the universe's hidden music, even if we're not yet sure the notes are real. Picture our universe not as an isolated bubble drifting through emptiness, but as a vast floating sheet, a membrane adrift in an unseen ocean of higher dimensions. This is the wild premise of brane world theory, where the cosmos we know might be just one of countless membranes or brains, vibrating in a space far grander than our 3 dimensions. It's like imagining a piece of paper suspended in midair, unaware that other papers might be hovering just inches away, each carrying its own entire reality. The idea took shape in the late 1990s when physicists Lisa Randall and Raman Sundram proposed that gravity's puzzling weakness could be explained if it weren't confined to our brain. While other forces like electromagnetism are tethered to our membrane, gravity might seep into the extra dimensions, diluting its strength in our world. Think of it like a soundproof wall. Light and matter stay trapped on our side, but gravity's vibrations leak through, making it feel faint by comparison. This single insight could solve one of physics' greatest riddles: why gravity is so absurdly weaker than the other fundamental forces. But the strangest twist: these neighboring branes might not stay politely separated. If another universe brane drifted close enough, the collision could send shockwaves through reality itself. Some researchers speculate that the Big Bang wasn't a singular explosion from nothing, but the aftermath of such a cosmic crash, a violent meeting of membranes that unleashed the energy to birth our universe. There's even a tantalizing hint in the cosmic microwave background, the afterglow of the Big Bang, where odd temperature fluctuations might bear scars from this primordial collision. What would happen if branes collided again? The possibilities range from the catastrophic, a new Big Bang wiping our universe clean, to the surreal. If a higher dimensional brane passed through ours, we might witness sudden, inexplicable changes in the laws of physics, as if reality itself glitched. Stars could flicker out, gravity might reverse, or entirely new forces could emerge without warning. It's a haunting thought. The stability we take for granted could be borrowed time, with other universes looming just beyond the veil. Yet for all its drama, brane world theory isn't pure speculation. Particle accelerators like the Large Hadron Collider hunt for evidence of extra dimensions by searching for particles that briefly disappear into higher dimensional space. Others study gravitational waves for anomalies that might ripple in from adjacent branes. Even if the theory remains unproven, it reshapes how we see the cosmos, not as a lonely island, but as one page in an infinite book, where turning the page might mean brushing against another universe entirely. What if everything you see, every star, every atom, even your own hands, is just a shadow cast by something far simpler? This is the essence of the holographic principle, an idea so radical it redefines reality itself. Imagine the universe as a vast, intricate projection, like light beaming from a cosmic movie reel. But instead of a three-dimensional world, the true film is flat, a two-dimensional surface encoding all the information needed to create our seemingly solid reality. It's not just a metaphor. Physicists have mathematical proof that this could be how the cosmos actually works. The roots of this idea trace back to black holes, those cosmic vacuum cleaners where gravity is so strong even light can't escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of its hidden information, isn't proportional to its volume as you'd expect, but to its surface area. Think of it like a holographic sticker, where a flat, shiny surface contains all the data needed to produce a three-dimensional image. Later, Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might operate the same way. The information needed to describe every particle, every force, even your thoughts, could be written on a distant boundary we'll never see, like code on the surface of an immeasurably vast sphere. But how could a flat surface project a 3D world? The answer lies in quantum entanglement, that spooky connection where particles instantly influence each other across vast distances. Entangled particles don't just link through space, they might stitch together the very fabric of reality, creating depth from flatness like a magician's illusion. Picture a million tiny threads, each one a quantum connection, weaving the pixels of our perceived world into existence. The screen you're staring at right now, the air you're breathing, it's all just an extraordinarily convincing rendering of data stored somewhere else. Here's where it gets even stranger. If the holographic principle is true, the universe has a finite resolution like a digital photo. Zoom in far enough and you'd hit the pixels of spacetime itself, where quantum fuzziness blurs the boundary between here and there. This could explain why black holes have a maximum entropy. They're not just swallowing matter, they're hitting the data storage limit of the cosmic hard drive. Even time might emerge from this flat information network, flowing like a video rendered frame by frame from static code. Skeptics argue the principle remains untested, a beautiful guess without experimental proof. Yet there are clues. In 2017, physicists simulating holographic universes on supercomputers found that gravitational effects in 3D spaces matched predictions from 2D models, as if reality really were a projection. Other experiments hunt for quantum entanglements, fingerprints in the cosmic microwave background, searching for patterns that might reveal the universe's hidden code. Whether the holographic principle holds up or not, it forces us to confront a humbling possibility. Reality might be thinner than we ever imagined, not just in substance but in structure, a shimmering surface masquerading as depth, a cosmic sleight of hand written in the language of quantum secrets. And if that's true, the next question is unavoidable. Who or what is holding the projector? What if the universe isn't just a cosmic accident, but a meticulously crafted simulation, a digital construct running on some unimaginably advanced computer? This is the simulation hypothesis, an idea that's equal parts thrilling and unsettling. Think of it like this: if humanity can already create virtual worlds with increasingly complex rules, video games, AI environments, even rudimentary simulations of quantum physics, then what's stopping a civilization billions of years ahead of us from building something infinitely more sophisticated? A universe like ours, rendered in flawless detail, with conscious beings who never suspect they're just lines of code in an alien supercomputer. The argument isn't just philosophical, it's rooted in probability. If simulating entire realities becomes possible, even commonplace, the number of simulated universes would vastly outnumber the original one. Statistically speaking, the odds that we're living in the base reality shrink to near zero. Elon Musk famously quipped that the chance we're not in a simulation is 1 in billions. Even renowned thinkers like Nick Bostrom have formalized this logic, suggesting that unless civilizations self-destruct before reaching simulation-capable technology, we're almost certainly living in someone else's experiment. But how would we even know? Some scientists propose that if our universe is a simulation, it might have detectable glitches, tiny imperfections in the fabric of reality where the programmers cut corners to save processing power. Imagine finding pixels in the cosmos, like a cosmic resolution limit where space becomes grainy at unfathomably small scales. Others hunt for anomalies in the laws of physics, like sudden changes in fundamental constants or mathematical patterns that hint at underlying code. One provocative study even suggested that if the universe is a simulation, high-energy cosmic rays might behave differently depending on which computational grid they're processed in, like a video game struggling to render distant objects. Then there's the eerie question of free will. If we're simulations, are our choices our own or just predetermined outputs of an algorithm? Some interpretations suggest that consciousness itself could be simulated without diminishing its reality. After all, if your thoughts feel real to you, does it matter whether they arise from neurons or nested subroutines? But others argue that true agency requires a base reality, raising unsettling implications about purpose and meaning. Critics dismiss the hypothesis as unfalsifiable, a modern twist on age-old solipsism dressed up in tech jargon. They point out that even if the universe behaves mathematically, that doesn't prove its artificial math might just be the language of reality, not its source code. Even the search for glitches faces a paradox. If the simulation is advanced enough, any errors we detect could be intentionally placed, or worse, deliberately inserted to lead us astray. Yet the hypothesis lingers, not just as a sci-fi trope, but as a lens to examine deeper questions. If consciousness can be simulated, does that make it less sacred or more? Could programmers be ethical deities or indifferent experimenters? And if we one day create simulations with sentient beings, does that make us their gods, their jailers, or something else entirely? Whether the hypothesis holds water or not, it forces us to confront the fragility of our assumptions. After all, the only thing more terrifying than being alone in the universe might be discovering we're not alone because we're someone else's invention. Time crystals sound like something ripped from a sci-fi novel, but they're very real, and they defy one of the most fundamental laws of physics. Normally, perpetual motion is impossible. The second law of thermodynamics insists that everything loses energy over time, winding down toward chaos. Yet time crystals flip this script. They're quantum systems that oscillate indefinitely, repeating their patterns like a clock that never needs winding, all without absorbing or dissipating energy. It's as if the universe carved out a tiny exception to its own rules, allowing these structures to dance forever in perfect, self-sustaining rhythm. The concept was first proposed in 2012 by Nobel Prize-winning physicist Frank Wilczek. He imagined a bizarre form of matter where atoms, instead of arranging themselves in repeating patterns in space like the lattice of a diamond, would also repeat their configurations in time. Picture a ring of particles that rotate, not because they're pushed by outside forces, but because their quantum interactions lock them into an eternal cycle. It's not motion in the traditional sense, it's more like the universe's background hum given physical form, a structure where time itself becomes part of the crystal's symmetry. Skeptics initially dismissed the idea as impossible, arguing it violated the laws of thermodynamics. But in 2017, two separate teams of scientists created the first time crystals in labs, using chains of charged atoms chilled to near absolute zero and manipulated with precise laser pulses. These crystals didn't just oscillate, they did so at a frequency unrelated to the energy input, a hallmark of their quantum weirdness. Unlike a pendulum which slows without a push, time crystals keep ticking even in their lowest energy state, as if the universe granted them a perpetual hall pass. So how do they cheat the system? The secret lies in what physicists call broken time symmetry. Most objects look the same whether you observe them now or 5 minutes later. A coffee cup doesn't spontaneously rearrange itself. But time crystals are different. Their atomic configurations shift predictably over time, repeating like the phases of the moon, even though no energy flows in or out. This isn't perpetual motion in the classic sense. It's more like the quantum equivalent of a record spinning on a turntable, where the needle never slows because the groove itself dictates the rhythm. What's truly mind-bending is what time crystals imply about the nature of time. If matter can lock into rhythms that don't decay, could there be pockets of the universe where time behaves differently? Some theorists speculate that time crystals might offer clues about quantum gravity or even the arrow of time itself. Others imagine harnessing their properties for fault-tolerant quantum computers, where information could be stored in their unbreakable cycles. Yet for all their promise, time crystals remain enigmatic. They exist only in highly controlled lab environments, and no one knows if natural versions lurk undiscovered in the cosmos. What's clear is this: they've shattered an assumption we didn't even realize was negotiable, that all motion must fade. In a universe relentlessly marching toward entropy, time crystals are the rebels that refuse to bow, proving reality still has tricks up its sleeve. Picture a substance so bizarre that instead of falling toward Earth, it pushes away, defying gravity not by floating gently, but by actively repelling everything around it. This isn't magic, it's negative mass, a hypothetical form of matter that would weigh less than nothing. If it exists, it wouldn't just bend the rules of physics, it would shatter them, unlocking possibilities like warp drives, perpetual motion machines, and even tunnels through space-time itself. The math behind negative mass is surprisingly straightforward, at least on paper. Einstein's equations allow for matter with negative gravitational charge, meaning it would repel ordinary mass while being repelled in return. Unlike antimatter, which has positive mass and behaves normally under gravity, negative mass would do the exact opposite, push a ball away, and it accelerates toward your hand instead of slowing down. Drop it and it might rocket skyward like a deflating balloon shot full of helium. even weirder, if you tied a chunk of negative mass to a spaceship, the pair would self-accelerate indefinitely, needing zero fuel, a literal free lunch from the universe's most stubborn rulebook. So where could such a substance be hiding? Some theorists suggest negative mass isn't just a quirk of equations. It might be the missing key to dark energy. If vast clouds of this exotic matter drifted through space, their mutual repulsion could drive the accelerating expansion of the cosmos, mimicking the effects we attribute to dark energy today. Others propose that negative mass could stabilize wormholes, those hypothetical shortcuts through spacetime. Normally, wormholes would collapse instantly under their own gravity, but a lining of negative mass might prop them open like an invisible scaffold, turning science fiction's favorite plot device into a genuine engineering problem. The catch: no one's ever observed negative mass in nature, and lab attempts to simulate it are shaky at best. In 2017, physicists created a fluid with effective negative mass by chilling rubidium atoms to near absolute zero and manipulating them with lasers. Push the fluid and it flowed backward, but this was a quantum trick, not true negative mass. Skeptics argue that if such matter existed, it would have revealed itself through bizarre gravitational lensing or unexplained cosmic acceleration patterns. Yet the hunt continues because the payoff would be staggering. A universe where the energy crisis is solved by a fuel that literally accelerates itself, where black holes might be connected by traversable tunnels, and where gravity itself becomes a force we can shape instead of just endure. Whether negative mass remains a mathematical curiosity or becomes the next revolution in physics, one thing's certain: it proves that even our wildest ideas are bound by the universe's willingness to surprise us. After all, if matter can weigh less than nothing, what other impossibilities are waiting to be rewritten? Black holes aren't just cosmic vacuum cleaners, they might be cosmic wombs. Imagine our entire universe with its swirling galaxies and infinite expanse, nestled inside the singularity of a black hole born in some higher dimensional reality. It sounds like the plot of a trippy sci-fi novel, but this is black hole cosmology, a theory suggesting that every black hole could be the seed of a new universe, and our own cosmos might have sprung from one. The idea hinges on a strange quirk of Einstein's equations. When matter collapses into a black hole, the math suggests spacetime inside the event horizon flips inside out. Time becomes space-like and space becomes time-like, creating conditions where the singularity isn't just a dead end, it's a big bang in disguise. Picture a funnel turning inside out. The narrow end, where everything seems to crush into oblivion, becomes the starting point of an explosive expansion. In this scenario, the universe we inhabit isn't the first and only iteration of reality. It's just one link in an endless chain of cosmic rebirths. This isn't pure speculation. When physicists trace our universe's expansion backward to the Big Bang, they hit a wall, a singularity eerily similar to the ones lurking in black holes. Both are points of infinite density where the laws of physics break down. The difference: one explodes outward, birthing a cosmos, the other pulls inward, devouring everything. But what if they're two sides of the same coin? Some models suggest the information swallowed by black holes doesn't vanish but gets reprocessed into the fundamental parameters of a new universe. The gravity we experience, the speed of light, even the number of dimensions, all could be cosmic inheritance, handmade down physics from the black hole that birthed us. Here's where it gets even wilder. If black holes spawn universes, then our own might be riddled with them. Every star-devouring singularity in our skies could contain an entire cosmos, complete with its own stars, galaxies, and perhaps even life, all hidden behind an event horizon we'll never cross. It's a dizzying thought. We might be living inside a black hole nested within another universe, which itself is inside a black hole, like a set of infinitely regressing cosmic matryoshka dolls. But how would we test such a mind-bending idea? Some researchers look for imprints in the cosmic microwave background, subtle swirls or asymmetries that might hint at a parent universe's structure. Others study the quantum behavior of black holes, searching for signs that information isn't lost but encoded in the fabric of a newborn cosmos. Even gravity waves could carry clues. Certain frequencies might reveal echoes of the universe's black hole ancestry. Critics argue this theory trades one mystery for another, replacing the question of the Big Bang's origin with an unknowable higher dimensional reality. Yet it offers something profound, a vision of the cosmos where death and rebirth are woven into the laws of physics, where black holes aren't just tombstones but cradles. If true, it means every time a star collapses somewhere in the void, a new universe flickers to life in the darkness, and our own existence might be the proof. The universe isn't expanding, it's multiplying. Imagine space itself as a bubbling cauldron, where every new bubble that rises to the surface isn't just a pocket of air, but an entirely new cosmos with its own laws of physics. This is eternal inflation, a theory so vast it redefines not just our universe but reality itself. At its core is a simple yet staggering idea: the Big Bang wasn't a one-time event. It was a single spark in an endless fireworks show where new universes bud off from the fabric of space-time like droplets from an infinite waterfall. The engine behind this cosmic replication is a field called the inflaton. In the earliest moments after the Big Bang, this field drove space to expand exponentially faster than light, smoothing and stretching the universe into the vast, flat expanse we see today. But here's the twist: according to eternal inflation, most of that field never stopped stretching. Instead, patches of it occasionally relax into stable states, releasing their pent-up energy in localized bursts, each one a new Big Bang, each one birthing a self-contained bubble universe. Picture a block of Swiss cheese where the cheese is eternally inflating space, and every hole is a separate cosmos with its own unique physics. What's astonishing is how much these bubble universes could differ. When a pocket of space stops inflating, the energy of the inflaton field doesn't just vanish, it crystallizes into the fundamental constants of that bubble's reality. The strength of gravity, the mass of electrons, even the number of dimensions might emerge at random, like dice rolls in a cosmic casino. Some universes might have gravity so strong they collapse instantly, others could be so diffuse that stars never form. And somewhere in this infinite sprawl, there's a bubble where the dice landed just right for galaxies, planets, and life like us to exist. This isn't just theoretical poetry. Eternal inflation solves one of cosmology's biggest puzzles: why our universe seems so fine-tuned for life. If every possible combination of physical laws gets a universe, it's no surprise we find ourselves in one where conditions allow us to exist, a statistical inevitability rather than a miracle. But the theory goes even further. Some versions suggest that bubble universes can collide, leaving scars in the cosmic microwave background or even triggering secondary Big Bangs within each other. Astronomers have searched for these bruises in the sky, odd temperature variations that might be the cosmic equivalent of a dent from a neighboring universe bumping into ours. Yet eternal inflation isn't without controversy. Critics argue it's untestable, a beautiful idea forever beyond our reach. Since any other universes would be causally disconnected from ours, their light never crossing the infinite gulf between bubbles. Others propose alternative models where universes are born from black holes or higher dimensional brains, each with its own flavor of cosmic ancestry. But for all its unknowns, eternal inflation offers something profound. A vision of reality where beginnings and endings are illusions, where the cosmos is less a single story and more an endless library, each book written in a different language of physics. And if it's true, then every time you look up at the night sky, you're not just seeing stars, you're glimpsing one page in an infinite anthology, a single verse in a poem that never ends. They slip through your body by the trillions every second, ghostly particles so elusive they barely interact with anything at all. These are neutrinos, nature's most aloof messengers, born in the hearts of stars, supernova, and even the Big Bang itself. For decades, physicists thought they were massless, zipping through the cosmos at the speed of light without a care. But then came the bombshell: neutrinos do have mass. It's vanishingly small, a fraction of an electron's already tiny weight, but that whisper of mass cracks open a door to one of the universe's deepest mysteries. Why does anything exist at all? Here's the puzzle. When the universe burst into existence, matter and antimatter should have been created in equal amounts, instantly annihilating each other in a burst of pure energy. Yet somehow, matter won out by the slimmest margin, leaving behind the galaxies, planets, and us. Neutrinos might hold the key to this cosmic asymmetry. Unlike other particles, neutrinos have a bizarre quirk: they oscillate. An electron neutrino emitted by the Sun can morph into a muon or tau neutrino mid-flight, as if flipping between identities like a quantum chameleon. This oscillation only happens if neutrinos have mass, and it hints at physics beyond the standard model rules that might explain why matter outnumbers antimatter. One leading theory involves something called the seesaw mechanism. Imagine a playground seesaw where one side represents ultra-light neutrinos we detect, and the other side is an unimaginably heavy neutrino no experiment has ever seen. According to this idea, these heavy neutrinos, sterile neutrinos, could have decayed asymmetrically in the early universe, producing slightly more matter than antimatter. It's a delicate balancing act, a 1 in a billion imbalance that snowballed into everything we see today. Then there's the eerie case of neutrino-less double beta decay. Some atomic nuclei can, in theory, spit out 2 electrons and no neutrinos, a forbidden process that would prove neutrinos are their own antiparticles. If observed, it would mean neutrinos are unique among particles, blurring the line between matter and antimatter. Experiments like Germany's Majorana demonstrator and Japan's Camland Zen are hunting for this telltale signature in underground labs shielded from cosmic noise. A detection would rewrite textbooks, revealing how neutrinos help tilt the cosmic scales. But why are neutrinos so impossibly light? One radical idea suggests they're not even from our universe, that they're bulk particles leaking into our dimension from higher dimensional space, their mass diluted across unseen realms. Others propose that neutrino mass is tied to the Higgs field, the cosmic molasses that gives particles their weight, but with a twist we haven't yet grasped. Every neutrino that passes unnoticed through your hand is a silent witness to the universe's earliest moments, carrying secrets about why we're here at all. Whether through their oscillations, their possible Majorana nature, or their connection to undiscovered physics, these ghostly particles might be the faintest flicker of a much larger story, one where the fate of all matter hangs on a quantum whim. We've all grown up learning about the 4 fundamental forces that rule the universe: gravity holding planets in orbit, electromagnetism lighting up our cities, and the strong and weak nuclear forces binding atoms together or tearing them apart. But what if there's a 5th player in this cosmic game? A hidden force, subtle yet powerful enough to explain some of the universe's biggest mysteries: dark matter's invisible grip, the strange dance of galaxies, even the quantum quirks that defy Einstein's relativity. This isn't just speculation. From lab experiments to galactic observations, strange inconsistencies hint that our physics textbooks might be missing a chapter. Take dark matter first. Its gravitational pull is undeniable, but after decades of searching, we've found no trace of the particles that supposedly make it up. Could the answer lie not in invisible matter, but in an invisible force? Some theories propose a 5th force that only interacts weakly with ordinary matter, acting like a shadowy counterpart to gravity. Unlike gravity, though, this force might have a limited range, tugging at stars and gas clouds only over galactic distances. Picture two magnets separated by a sheet of paper. They attract, but place a book between them and the pull vanishes. A fifth force could work similarly, strong enough to sculpt galaxies yet fading to nothing on smaller scales, explaining why we've never felt its presence on Earth. Then there's the quantum world, where particles entangle across vast distances, seemingly communicating faster than light. Einstein called it spooky action at a distance, but what if it's not spooky, just a sign of something deeper? Certain extensions to the Standard Model, like hidden sector theories, suggest undiscovered forces could mediate these bizarre connections. These forces wouldn't rely on photons or gluons, the usual force carriers, but on exotic particles that pass through our reality like whispers through a wall. Experiments like the Arizona Dark Matter Detector hunt for faint recoils caused by such particles, while others study neutron stars for anomalies in their gravitational waves that might betray a fifth force's influence. But the boldest ideas come from attempts to unite quantum mechanics and gravity. String theory and loop quantum gravity both stumble over how to mesh gravity's smooth spacetime with quantum frenzy. A fifth force could bridge the gap, a kind of quantum glue that stitches spacetime together at the smallest scales. Some models even suggest this force might manifest as tiny repulsion between particles, counteracting gravity on quantum levels and preventing singularities from forming. In this light, black holes might not crush matter into infinite density, but reach a point where the fifth force pushes back, creating something entirely new. Critics argue that adding a fifth force complicates physics without definitive proof, yet history shows science often advances by chasing irregularities. The planet Uranus' wobbly orbit revealed Neptune's existence. Mercury's precession hinted at relativity. Today's anomalies, like the muon G2 experiments, baffling results, or certain galaxies rotating too fast, might be tomorrow's breakthroughs. Whether the fifth force is a cosmic illusion or a paradigm shift, the search itself is a reminder. The universe still has rules we've yet to read. Gravity might not be what we think it is. Forget Newton's apple or Einstein's warped spacetime. What if gravity isn't a fundamental force at all, but something that emerges from the chaotic, invisible chatter of quantum information? This is the radical premise of emergent gravity, a theory that rewrites the cosmic rulebook by suggesting gravity isn't a primary player. Instead, it's more like temperature, a collective effect that arises from something deeper, like how the warmth of a cup of coffee emerges from the frantic dance of countless molecules. The idea traces back to an unexpected source: black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, its hidden information, is proportional not to its volume but to its surface area. This odd link between information and geometry hinted at something profound. Decades later, researchers like Eric Verland took it further, proposing that gravity itself might be an illusion, a side effect of quantum entanglement, those spooky connections where particles instantly influence each other across vast distances. Imagine the universe as a vast cosmic computer, where every particle, every bit of matter is entangled in an invisible network. Gravity, in this view, isn't a force transmitted through space but a statistical tendency, like the way a crowd's murmurs merge into a single roar. Here's how it might work. Picture spacetime as a fabric woven from countless quantum bits or qubits. When matter enters this fabric, it disrupts the entanglement patterns around it, creating a kind of information imbalance. The surrounding qubits scramble to rebalance themselves, and this collective adjustment manifests as what we perceive as gravity. It's not that massive objects pull each other, it's that their presence distorts the underlying information landscape, and the universe's natural tendency toward equilibrium creates the illusion of attraction. Think of it like a trampoline sagging under a bowling ball. We see the dip as gravity, but in reality, it's just the fabric's way of reconfiguring itself to accommodate the new data. This isn't just abstract theorizing. Emergent gravity offers elegant solutions to some of cosmology's thorniest problems. Take dark matter, for example. Instead of invoking invisible particles, Verland's equations suggest that the extra gravitational tug we attribute to dark matter might arise from the way galaxies disrupt the entanglement structure of spacetime itself. Certain galaxies' rotation curves, which don't match predictions based on visible matter, align neatly with emergent gravity's math, no exotic particles required. Similarly, the theory could explain why gravity is so mind-bogglingly weak compared to other forces. If it's not fundamental but emergent, its feebleness makes sense. It's not a primary interaction, just a secondary echo of quantum information processing. Of course, not everyone's convinced. Critics point out that emergent gravity struggles to explain phenomena like gravitational waves or the precise motions of galaxy clusters. And without a way to directly observe the quantum entanglement underlying spacetime, the theory remains tantalizingly untested, yet experiments are inching closer. Some researchers propose that subtle anomalies in gravitational wave signals or deviations in the bending of starlight could reveal spacetime's informational scaffolding. Others are simulating quantum networks to see if gravity-like behavior spontaneously arises from entangled systems. Whether emergent gravity ultimately holds up or not, it forces us to confront a dizzying possibility. The universe might not run on forces and fields at all, but on something far stranger: information itself. In this view, reality isn't built from particles or waves, but from relationships, from the invisible threads connecting every bit of existence. And if that's true, then gravity isn't the hand that shapes the cosmos. It's just the shadow of something deeper, a cosmic conversation we're only beginning to overhear. Black holes devour everything in their path, but what if the universe has cosmic fountains that do the exact opposite? White holes, their mysterious theoretical twins, are like black holes running in reverse. Where a black hole's gravity traps even light, a white hole violently repels it, spewing out matter and energy like an unstoppable geyser. Imagine a celestial fire hose blasting particles into space with such force that nothing, not even a spaceship traveling at light speed, could force its way inside. While black holes are cosmic prisons, white holes would be fortresses with no entrance, only exits. And if they exist, they might not just be oddities. They could be the universe's way of recycling reality itself. The math behind white holes is just as real as black holes. In fact, they emerge naturally from Einstein's equations. If you rewind a black hole's collapse in time, you get a white hole, a singularity that eternally expels everything it contains. Some theories even suggest that when a black hole dies through processes like Hawking radiation, it could transform into a white hole, releasing all the information it once swallowed. Picture a star collapsing into a black hole, only to rebound eons later as a radiant fountain, its trapped energy flooding back into the cosmos. This quantum bounce idea offers a tantalizing solution to the black hole information paradox, the puzzle of whether data swallowed by black holes truly vanishes forever. But the wildest possibility, white holes might not just be endpoints, they could be starting points. Some cosmologists propose that the Big Bang itself was a white hole event, a primordial explosion not from a single point of infinite density, but from the throat of a higher dimensional white hole in another universe. In this scenario, our entire cosmos could be the other side of a black hole from a parent universe, with the Big Bang's fireball being the moment that black hole's interior rebounded outward. It's a dizzying thought. Every galaxy, every atom might trace its lineage to a cosmic eruption in a reality we'll never see. Yet for all their theoretical elegance, white holes face a glaring problem. No one's ever seen one. Their very nature makes them unlikely to last long. Any matter they emit would eventually fall back toward their own gravity, collapsing the white hole into a black hole, unless some unknown quantum effect stabilizes them. Some astrophysicists speculate that fleeting white holes could explain mysterious high-energy events like gamma-ray bursts, those universe-spanning flashes brighter than a billion suns. Others wonder if dark matter's gravitational effects could hint at ancient white holes lingering unseen, their outbursts long faded but their mass still warping space. Whether cosmic myths or hidden architects of reality, white holes challenge our assumptions about time, entropy, and the universe's resilience. They remind us that even the most voracious monsters in the cosmos might, somewhere or someone, have a second act, a rebound waiting in the dark. What if your thoughts could shape reality itself, not through willpower or coincidence, but because consciousness is woven into the very fabric of quantum mechanics? This isn't mysticism, it's the pulse of a radical idea called quantum consciousness, where the mind might play an active role in collapsing the universe's infinite possibilities into a single, tangible reality. At the heart of this controversy lies the famous double-slit experiment, where particles behave as waves when unobserved, spreading out in probabilities, but snap into definite positions the moment they're measured. The unsettling implication, the act of observation itself might determine reality's course. Take the most startling interpretation, the von Neumann-Wigner hypothesis, which dares to suggest that consciousness isn't just observing quantum events, it's creating them. In this view, the probabilistic fog of quantum mechanics only solidifies when encountering a conscious mind. Picture ripples in a pond that remain shimmering possibilities until a fish, the observer, looks at them, forcing the water to choose a single shape. Critics argue this veers into solipsism, but proponents point to experiments like the quantum Zeno effect, where rapidly observing an unstable particle can prevent its decay, as if attention itself holds reality in place. Then there's orchestrated objective reduction, ORCH, or a theory by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness arises from quantum vibrations within microtubules, tiny protein structures in brain cells. These vibrations, they argue, aren't just biological noise but quantum computations that collapse into conscious moments. When anesthesia dampens these vibrations, consciousness flickers out, like a quantum computer powering down. It's a bold claim that our thoughts might be quantum processes dancing between possibilities until observation pins them down, but the wildest twist. Some interpretations suggest quantum consciousness could bridge the gap between mind and cosmos. If observation shapes reality, then the universe might need conscious observers to bring it into full existence, a cosmic chicken and egg paradox where sentience and physics co-create each other. The implications spiral outward. Could artificial intelligence, if conscious, collapse quantum states? Could collective human thought influence matter on a macro scale? Decades of failed attempts to mentally alter quantum experiments like the Princeton pair trials cast doubt, yet the mystery lingers. Skeptics counter that decoherence, quantum interactions with the environment, explains wave function collapse without invoking consciousness. But the debate isn't just academic. If even a sliver of these ideas holds truth, it redefines everything from free will to the nature of existence. Whether quantum consciousness is a profound insight or a category error, it forces us to confront a haunting question. Are we passive witnesses to the universe or unwitting architects? Picture the universe as a frozen lake on a winter morning, seemingly solid, stable, an unchanging expanse where we skate across without a second thought. But beneath that deceptive surface, there might be a terrifying truth. Our reality is balancing on a knife's edge, one quantum nudge away from instant annihilation. This is the false vacuum hypothesis, the idea that what we call empty space isn't truly empty nor truly stable. Instead, it could be a precarious ledge suspended above a deeper, truer state of nothingness, and the slightest tremor could send everything tumbling into oblivion. At the heart of this theory lies the Higgs field, the invisible energy ocean that gives particles their mass. Like all quantum fields, it's thought to have a lowest energy state, a true vacuum where it's perfectly calm. But what if the Higgs field in our universe hasn't settled there yet? What if it's temporarily trapped in a higher energy, false vacuum, like a ball resting on a hillside instead of rolling to the valley below? The consequences of that ball finally slipping would be apocalyptic. A bubble of true vacuum could form anywhere in space, expanding at the speed of light, rewriting the laws of physics as it goes. One moment you're sipping coffee, the next atoms themselves cease to function, dissolving reality into something unrecognizable, or worse, into absolute nothingness. The math behind this scenario is chillingly plausible. Quantum fluctuations happen constantly, and given enough time, say, trillions of years, statistics suggest one could finally knock the Higgs field over the edge. There's no warning, no defense. The trigger could be as random as a high-energy particle collision in deep space, or even an experiment in a particle accelerator like CERN. Once the process starts, it's unstoppable. The bubble's wall would be a boundary beyond which physics as we know it no longer applies, erasing stars, civilizations, and even time itself in its path. The universe wouldn't just end, it would be replaced with no guarantee the new rules would allow for matter, light, or life. Yet here's the twisted silver lining. If this nightmare scenario is possible, it hasn't happened yet. That either means we're in the unimaginably lucky early moments before the dice finally roll against us, or just maybe our vacuum is truly stable after all. Recent measurements of the Higgs boson's mass hint that we might be closer to the edge than physicists once thought, balanced in a metastable state that could last for eons or collapse tomorrow. The uncertainty is part of what makes this threat so haunting. Unlike asteroid impacts or supernova, there's no way to prepare, no way to see it coming. It's a cosmic game of Russian roulette where every moment of existence is another pull of the trigger that hasn't fired yet. So why hasn't this vacuum decay already happened elsewhere in the cosmos? One grim possibility is that it has, and those universes are already gone, leaving no trace behind. Alternatively, the sheer size of space might mean the dice just haven't landed the wrong way in our corner of reality. Or perhaps there's a deeper law of physics preventing decay, some undiscovered principle that keeps the universe locked in its current state. Until we know for sure, the false vacuum remains the ultimate existential gamble, a reminder that the ground beneath our feet and the space between the stars might be far more fragile than it seems. Black holes aren't the end, they might be cosmic phoenixes, collapsing not into infinite oblivion but reborn as something even stranger. Deep inside the crushing grip of a black hole's singularity, where gravity warps space-time beyond recognition, quantum physics whispers a counterintuitive possibility. Instead of matter disappearing forever, it could bounce back, squeezed into an object so dense it defies imagination, a Planck star. Picture a dying star collapsing inward, reaching densities so extreme that the very fabric of space rebels. At the tiniest scales, quantum effects would kick in like an unstoppable spring, reversing the collapse in a violent rebound. The result, a luminous, ultra-compact orb just a trillionth the size of an atom, yet containing the mass of an entire star, blazing with the energy of its resurrection. This isn't science fiction, it's a prediction of loop quantum gravity, a framework where space-time isn't smooth and continuous but woven from indivisible threads. In this view, gravity's crushing force has a limit. Once matter is compressed to the Planck scale, the smallest possible unit of space, it hits a quantum wall. Think of it like compressing a spring to its absolute limit. Push any further, and it snaps back with unstoppable force. For a collapsing star, this means the singularity isn't a dead end but a cosmic trampoline, launching its mass back outward as a Planck star. The rebound wouldn't happen slowly. It would be a cataclysmic event, unleashing energy comparable to the black hole's formation but in reverse, a white-hot echo of stellar death. Here's where it gets even wilder. Because this rebound occurs inside the black hole's event horizon, we'd never see it directly from the outside, but the effects might still ripple across the cosmos. Some theories suggest that Planck stars could be the hidden engines behind fast radio bursts, those mysterious, millisecond-long blasts of energy that flash across the universe. Others speculate that the radiation from a Planck star's rebirth might subtly alter the Hawking radiation leaking from black holes, leaving faint fingerprints in the quantum static of deep space. There's even a tantalizing idea that some dark matter could be made of ancient Planck stars, lingering like cosmic ghosts from black holes that bounced back long ago. Of course, the Planck star hypothesis isn't without controversy. Traditional relativity insists singularities are points of no return where physics breaks down entirely. Detecting a Planck star's signature would require peering past the event horizon, a feat that seems impossible by today's technology. Yet the mere possibility reshapes how we see black holes not as graves but as cocoons. If matter can rebound from the edge of annihilation, then destruction and creation might be two sides of the same coin, woven into the quantum fabric of the universe itself. Whether Planck stars are real or not, they remind us that even in the darkest corners of space, there's always a chance for rebirth. Dark matter remains the universe's most frustrating hide-and-seek champion, elusive, invisible, and seemingly untouchable. But what if part of the reason we can't find it isn't just because it's hiding, but because it's changing? Enter chameleon particles, a hypothetical form of dark matter so cunning it adapts to its surroundings like a cosmic shapeshifter. Unlike traditional dark matter candidates that stubbornly refuse to interact with light or matter, chameleon particles would have a far more devious trick. Their mass isn't fixed. In dense environments like Earth's atmosphere or lab detectors, these particles could become nearly weightless, slipping through experiments undetected. But in the emptiness of interstellar space, their mass might balloon, giving them the gravitational heft needed to sculpt galaxies. The idea hinges on a concept called screening, where certain particles adjust their properties based on local conditions. Picture a spy who changes their appearance depending on the neighborhood, wearing a lab coat in a research facility, then swapping to celestial robes in deep space. For chameleon particles, this adaptability would explain why Earthbound detectors keep coming up empty. If their mass shrinks to near zero near matter, they'd breeze past sensors like ghosts through walls. But in the void between galaxies, where matter is scarce, they'd regain their full gravitational strength, tugging stars and bending light just as astronomers observe. This isn't just a clever workaround, it's a radical reimagining of how dark matter might behave. Traditional searches assume dark matter particles are static, like WIMP weakly interacting massive particles, which should occasionally bump into atomic nuclei in underground detectors. Chameleon particles, though, would actively avoid detection, their mass shifting dynamically to stay hidden. Some theories even suggest they could be linked to dark energy, with their variable mass influencing the expansion of the universe itself. Imagine a cosmic thermostat where the particle's behavior tunes the balance between gravity's pull and dark energy's push, all while staying just out of sight. Testing this idea requires equally creative experiments. Instead of waiting for dark matter to collide with detectors, physicists are designing sensors that mimic the sparse environments of deep space, hoping to catch chameleon particles off guard. One approach involves ultra-sensitive force probes placed in vacuum chambers, where the absence of matter might coax the particles into revealing their true mass. Others look for subtle anomalies in the orbits of distant stars or the clustering of galaxies, hunting for patterns that suggest dark matter's strength changes with its surroundings. The implications are staggering. If chameleon particles are real, they'd rewrite not just the dark matter playbook but our understanding of particle physics itself. A substance that morphs to evade capture challenges the very definition of matter, blurring the line between particle and field, between substance and shadow. Whether these shape-shifters exist or not, their possibility reminds us that the universe's secrets might not just be hidden. They could be hiding in plain sight, disguised as nothing at all. Deep inside the corpse of a dead star, the universe keeps shaking. Neutron stars, those ultra-dense remnants of supernova explosions, aren't just inert cosmic tombstones. Their surfaces can crack like planetary crusts, sending violent tremors rippling through space-time itself. These starquakes aren't ordinary tremors. When a neutron star's crust, a crystalline layer 10 billion times stronger than steel, suddenly fractures, it releases enough energy to briefly outshine the entire Milky Way. But the real marvel isn't the flash. It's what happens next. The quake sends gravitational waves pulsing across the cosmos, carrying secrets about the most extreme states of matter in existence. The physics behind these quakes is almost otherworldly. A neutron star's crust is under unimaginable strain, squeezed by gravitational forces so intense that a sugar cube-sized chunk would weigh as much as a mountain. Yet this crust floats on an ocean of superfluid neutrons, a bizarre quantum soup that flows without friction. When the star's insane rotation, some spin hundreds of times per second, or sudden magnetic shifts stress the crust beyond its breaking point, it snaps. The resulting quake can shift the star's entire surface by centimeters, trivial on Earth, but catastrophic when that crust is packed tighter than an atomic nucleus. That tiny slip unleashes pent-up energy equivalent to 100 billion nuclear bombs, vibrating the star like a bell and warping the fabric of space-time around it. These distortions aren't just theoretical. In 2017, gravitational wave detectors like LIGO and Virgo began picking up faint ripples that might match neutron star quakes. The signals differ from black hole mergers. They're shorter, sharper, like a cosmic drumbeat rather than a collision's crescendo. Some researchers speculate that certain gamma-ray bursts, those mysterious flashes of high-energy light, could be the electromagnetic counterparts to these gravitational shudders, the visible echo of a star's crust cracking under pressure. But the true prize lies in what these quakes reveal about neutron star interiors. The vibration's frequency and decay rate act like a sonogram, probing depths we'll never physically reach. Some patterns hint at hyperons or free quakes swimming in the core exotic states of matter that defy earthly chemistry. Others suggest nuclear poster, a bizarre form of matter where protons and neutrons arrange themselves into shapes like spaghetti or lasagna sheets under extreme pressure. Every quake is a message in a bottle, tossed from a realm where the rules of physics are rewritten daily. The wildest possibility, some neutron stars might harbor mountains, not rocky peaks, but microscopic imperfections on their otherwise perfect spheres. These bumps, no taller than a fingernail's width, could create persistent gravitational waves as the star spins. Future detectors like the space-based LISA might hear this eternal hum, a choir of dead stars singing in space-time. Whether through violent quakes or subtle deformations, neutron stars are anything but silent. They're cosmic laboratories, broadcasting experiments we're only beginning to decode, one ripple at a time. At scales a billion times smaller than an atom, the smooth fabric of space-time we take for granted dissolves into chaos, a churning ocean where reality itself boils with fleeting particles and microscopic wormholes. This is quantum foam, the frenzied foundation of existence predicted by physicist John Wheeler in the 1950s. Imagine zooming in on empty space until what seems like perfect stillness erupts into a storm of virtual particles popping in and out of existence, warping space-time into fleeting hills and valleys so extreme that even concepts like here and now lose meaning. The foam emerges from Heisenberg's uncertainty principle, which allows energy to materialize from nothing provided it vanishes again almost instantly. These quantum fluctuations aren't just mathematical quirks. They're as real as the screen you're staring at, proven by effects like the Casimir force, where metal plates placed nanometers apart feel a measurable push from the foam's seething energy outside them. But the true strangeness lies deeper. At the Planck scale, distances of 10 to the power of -35 meters space-time might not even be continuous. Instead, it could behave like the froth on a cappuccino, with bubbles of distorted geometry constantly forming and dissolving. In this realm, tiny wormholes might bridge disconnected points, while black holes smaller than atoms blink into existence and vanish before anything can cross their event horizons. Some theories suggest the foam isn't random noise but a dynamic network, with entangled quantum connections threading through it like invisible silk. These threads might underpin everything from gravity to the speed of light, acting as the hidden scaffolding of physical laws. Ripples in the foam could even explain dark energy, with the universe's accelerating expansion driven by the cumulative effect of countless microscopic spacetime fluctuations. It's as if reality is built on shifting sands, its apparent stability an illusion maintained by statistical averages across unimaginable scales. Yet the foam remains frustratingly out of reach. Probing it directly would require particle colliders the size of solar systems, and even our sharpest quantum sensors only glimpse its shadow. Still, clues might hide in high-energy cosmic rays or anomalies in gravitational wave data. If we ever decode its language, we might find that the universe isn't just stranger than we imagine, it's stranger than we can imagine, with every quiet moment of empty space concealing a tempest of creation and destruction. What if dark matter isn't just a sea of invisible particles, but an entire shadow universe with its own hidden forces, its own light, even its own versions of stars we can't see? That's the tantalizing premise behind dark photons, hypothetical particles that could serve as the messengers of a secret electromagnetic force, one that operates entirely in the dark sector. While ordinary photons mediate the familiar push and pull of light and electricity, dark photons would carry interactions between dark matter particles, weaving an unseen web of influence parallel to our own. The idea emerged from a simple but profound question. If dark matter truly makes up 85% of the universe's matter, why should it interact only through gravity? Normal matter doesn't play by such limited rules. It experiences electromagnetism, the strong and weak nuclear forces. Why wouldn't dark matter have its own rich physics? Dark photons offer a solution, acting as the glue for a hidden ecosystem where dark particles attract, repel, or even form exotic structures via their own version of electromagnetism. Picture an invisible city humming with activity right beside our own, its streets and buildings made of dark atoms illuminated by dark light, all governed by laws eerily similar yet utterly alien to ours. Searching for these phantom particles isn't just theoretical curiosity, it's a detective story with real stakes. If dark photons exist, they might occasionally mix with ordinary photons, leaving faint traces in high-precision experiments. Particle colliders like CERN have hunted for these signals by smashing beams of electrons together and watching for unexpected energy losses, potential signs that some energy leaked into the dark sector. Other setups use powerful magnets to coax dark photons into revealing themselves through minuscule anomalies in particle behavior. In 2020, an experiment at Italy's Gran Sasso lab reported a tantalizing blip in their data, a flicker that could have been a dark photon's whisper, though follow-ups have yet to confirm it. Yet the implications go far beyond particle physics. If dark photons bridge our world and the dark sector, they could explain cosmic anomalies like the galactic gamma ray, excess mysterious high-energy light radiating from the Milky Way's core, which some theorists argue might be dark matter particles annihilating via dark photon intermediaries. Even more radical is the possibility that dark photons could unlock technologies beyond our wildest sci-fi dreams. If harnessed, a dark electromagnetic force might allow communication or energy transfer through entirely new channels, untouched by the limits of our known physics. Skeptics counter that dark photons remain speculative, with no definitive proof after decades of searching. but that's the nature of frontier science. The hunt itself reshapes our understanding, even in failure. Whether dark photons are real or not, they remind us that the universe's greatest secrets might not lie in the voids between stars, but in the shadows between the forces we think we know. Neutrons should be predictable after all. They're one of the universe's most fundamental building blocks. When left alone outside an atom, they decay into a proton, an electron, and a neutrino in about 15 minutes, like clockwork. At least that's what the textbooks say, but something's off. Recent experiments have caught neutrons behaving strangely, decaying at slightly different rates depending on how they're measured. These tiny discrepancies might seem insignificant, but in the world of particle physics, they're seismic, hinting at forces or particles we've never seen before, quietly tugging at the fabric of reality. Take the beam versus bottle mystery. When scientists track neutrons zipping through a particle beam, their average lifespan clocks in around 14 minutes and 48 seconds. But when neutrons are trapped in a magnetic bottle, drifting in isolation, they last nearly 10 seconds longer. 10 seconds might not sound like much, but in the subatomic realm, it's an eternity, an inconsistency that shouldn't exist if our understanding of physics is complete. The numbers stubbornly refuse to align, as if neutrons are playing by different rules depending on how we observe them. One tantalizing explanation, a fourth flavor of neutrino, dubbed the sterile neutrino, slipping undetected through our experiments. The three known neutrinos, electron, muon, and tau, are already ghostly enough, barely interacting with matter. A sterile neutrino would be even more elusive, ignoring every force except gravity. If neutrons occasionally decay into these shadowy particles, they'd carry away energy without leaving a trace, subtly altering the measured decay rates. It's like a magician's trick where the sleight of hand happens in dimensions we can't see, but the plot thickens. Some theorists propose that the anomaly isn't a particle at all, but a glimpse of dark matter's hidden influence. If dark matter interacts weakly with neutrons, perhaps through a previously unknown force, it could nudge their decay rates in ways that vary with experimental setups. Picture a game of billiards where invisible hands occasionally bump the balls, steering outcomes just outside the expected range. Others speculate that quantum gravity effects, normally negligible at particle scales, might distort neutron behavior in ways we're only starting to detect. Then there's the wild card. What if the discrepancy points to flaws in our bedrock theories? The standard model of particle physics has survived every test thrown at it for decades, but neutron decay anomalies could be the first cracks in its foundation. Perhaps there's a deeper layer of physics where forces we haven't yet named flicker in and out of existence, tweaking the rules when we're not looking. For now, the mystery remains unsolved. Labs worldwide are refining their measurements, using ultra-cold neutrons and precision traps to chase down every possible error. Some hope to catch a whiff of sterile neutrinos. Others hunt for irregularities in the energy spectra of decay products, searching for missing pieces in the puzzle. Whatever the answer, one thing's certain: the humble neutron, once considered a well-mapped corner of physics, has become a frontier. And at the edges of our understanding, even the smallest anomalies can lead to the biggest revolutions. Imagine a cosmic mirror where every particle we know, electrons, quarks, even the elusive Higgs boson, has a hidden twin, a heavier and more exotic counterpart lurking just beyond our reach. This isn't multiverse fiction, it's the audacious promise of supersymmetry, a theory so mathematically beautiful it's been called the diamond of particle physics. At its heart lies a startling symmetry. For every known particle, there should exist a superpartner, a shadow version with eerily similar properties but different quantum spins. Electrons would be paired with selectrons, quarks with squarks, and photons with photinos. These twins aren't just duplicates, they're the missing pieces that could solve some of physics' greatest puzzles, from dark matter's identity to the baffling weakness of gravity. The elegance of supersymmetry lies in its power to tidy up the universe's messy math. In the Standard Model, particles like the Higgs boson should have absurdly high masses due to quantum corrections, so high, in fact, that the universe as we know it couldn't exist. Superpartners act as cosmic counterweights, cancelling out these infinite terms with surgical precision. It's like balancing a ledger where every particle's excess is offset by its twin, restoring order to the equations. This symmetry isn't just convenient, it's almost too perfect, as if the universe whispered a secret formula to mathematicians and dared them to prove it real. Yet the theory's most tantalizing gift might be its dark matter candidate, the lightest superpartner, often dubbed the neutralino. Unlike ordinary matter, neutralinos would be stable, electrically neutral, and barely interact with light, matching dark matter's elusive profile. If they exist, they could be drifting through your body right now, their collective gravity sculpting galaxies while remaining utterly invisible. Supersymmetry doesn't just predict these particles, it demands them, offering a natural home for the universe's missing mass. But where are all these superpartners, despite decades of hunting, with particle colliders like the LHC scouring energy ranges where supersymmetry suggested they'd appear? No squarks, photinos, or neutralinos have shown up. This absence has forced physicists to tweak the theory, pushing superpartner masses into higher, less accessible energy realms. Critics argue this flexibility makes supersymmetry unfalsifiable, a theory that can always retreat to safer ground. Still, the hunt isn't over. Supersymmetry could manifest in subtler ways. Perhaps superpartners are just beyond our current collider's reach, or maybe they decay too quickly to spot. Some experiments search for indirect hints, like anomalies in rare particle decays or unexpected cosmic ray patterns. Others explore split supersymmetry, where only certain superpartners remain light enough to detect. Whether the theory survives or falls, its legacy is secure, a daring vision of cosmic balance that pushed physics to ask deeper questions, even if the answers remain hidden in the shadows. The universe's infancy wasn't a smooth, gentle birth. It was a turbulent explosion of phase transitions, like water freezing into ice across the fabric of space-time itself. And just as cracks form in freezing lakes, these cosmic shifts might have left behind scars. Cosmic strings, hypothetical defects thinner than an atom but stretching across the entire observable universe. Picture these structures as unimaginably dense threads of pure energy, remnants of a time when the fundamental forces hadn't yet settled into their current forms. Unlike black holes or stars, cosmic strings wouldn't be made of matter. They'd be kinks in space-time itself, flaws in the cosmic diamond where the rules of physics briefly glitched. What makes them so bizarre is their sheer gravitational might. A single cosmic string just 6 miles long could weigh as much as the entire Earth, its mass concentrated into a line so narrow it'd slice through planets like a hot wire through butter. But here's the twist: despite their density, these strings wouldn't pull objects inward like ordinary gravity. Instead, they'd warp space in a way that creates mirror image distortions on either side. Sail past one in a spaceship and you wouldn't feel a tug. You'd suddenly find yourself staring at a duplicate of your own vessel, a ghostly counterpart created by the string's gravitational lensing. It's as if the universe folded around the defect, stitching reality together in a way that defies intuition. The wildest possibility: cosmic strings might not be static. Some theories suggest they could oscillate whip-like at near light speed. When two strings crossed, they might interlink like spaghetti strands or snap violently, releasing bursts of gravitational waves detectable across billions of light years. Even stranger, a loop of cosmic string could collapse into a black hole, or, if the math holds, form a traversable wormhole, a backdoor through space-time held open by the string's exotic physics. These aren't just abstract ideas. In 2021, astronomers spotted a peculiar hexagon of distant galaxies far too large and symmetrical to form naturally. One tantalizing explanation: light from those galaxies bent around a cosmic string's invisible filament, warping our view into a geometric mirage. Yet for all their theoretical allure, cosmic strings remain elusive. Unlike black holes, they wouldn't emit light or swallow matter, leaving almost no trace unless we know where to look. Gravitational wave observatories might catch the ripples from snapping strings, while telescope surveys could reveal strange, linear patterns in the cosmic microwave background. Some physicists even propose that strings, if they exist, might explain the universe's largest structures, those vast, filamentary webs of galaxies stretching across the void. After all, what better scaffolding for a cosmic web than defects woven into spacetime at the dawn of time? Whether relics of a fractured infancy or mathematical phantoms, cosmic strings force us to confront a humbling truth. The universe might be stitched together with flaws we can't yet see, flaws that could rewrite the very geometry of reality. Crushed under pressures so immense they defy comprehension, the cores of neutron stars don't just bend the rules of physics, they rewrite them entirely. Here, at densities 100 trillion times greater than steel, atomic nuclei cease to exist. Protons and electrons fuse into a seething ocean of neutrons, packed shoulder to shoulder like sardines in a cosmic can. But descend deeper past this neutron-rich crust, and matter undergoes a metamorphosis even more extreme. The very neutrons themselves, normally stalwart particles, get pulverized into their primordial ingredients, a roiling, hyper-dense broth of quarks and gluons known as quark-gluon plasma. This isn't just theorized exotic matter, it's a fleeting state that hasn't existed widely since the universe was a split second old. What makes this plasma so bizarre is how it shatters everything we know about matter's structure. Under everyday conditions, quarks, the building blocks of protons and neutrons, are perpetually bound together by gluons, the sticky particles of the strong nuclear force. No amount of earthly force can separate them. It's why we've never observed a lone quark in isolation. But in a neutron star's core, gravity wins this tug of war. The weight of 500,000 Earths pressing downward overcomes the strong force's grip, literally squeezing neutrons until they burst like overfilled water balloons. Their quarks spill out, mingling freely in what physicists call a strange soup, a fluid with zero viscosity, infinite thermal conductivity, and properties closer to a liquid than a gas, despite existing at temperatures of trillions of degrees. The implications ripple outward. Some models suggest this quark-gluon soup might crystallize into even weirder phases, like color superconductors, where quark pairs flow without resistance in patterns governed by quantum chromodynamics rather than ordinary electromagnetism. Others propose that certain neutron stars, those above about 2 solar masses, might be almost entirely composed of this plasma, making them not true neutron stars at all, but quark stars in disguise. These hypothetical objects would be even denser than their neutron-rich cousins, with a surface so smooth and frictionless that mountains couldn't form, leaving them eerily perfect spheres spinning in the void. Yet the wildest twist concerns strange quarks, a heavier, unstable cousin of the up and down quarks that make up normal matter. Under extreme pressures, ordinary quarks might transition into strange quarks, creating strange matter, a substance so stable it could theoretically infect normal matter on contact, converting neutrons into strange quarks in a chain reaction. If true, certain neutron stars might be ticking time bombs, their cores capped by a thin crust that, if ruptured by a collision or quake, could trigger a strange-lit apocalypse, transforming entire stars into strange matter in a catastrophic phase change. Probing these theories isn't just about satisfying curiosity. Recreating quark-gluon plasma here on Earth, as they've done fleetingly in particle colliders like the RIC and LHC, gives us snapshots of the universe's first microseconds. But those lab-made plasmas last for less than a heartbeat before dissipating. Neutron star cores, by contrast, are nature's pressure cookers, sustaining these conditions for millennia. By studying their gravitational waves, X-ray emissions, and even occasional explosive mergers, we're glimpsing a regime where matter isn't just compressed, it's reduced to its most primal, perfect form. Every pulse from these stellar corpses carries encrypted bulletins from a realm where the rules are written in quarks, not atoms, a reminder that what we call normal is just one note in a far grander cosmic symphony. Imagine holding a piece of the cosmos in your hand, not a rock from the moon or a shard of meteorite, but a material engineered to bend light like a black hole or warp space like a wormhole. This isn't science fiction, it's the cutting edge of vacuum metamaterials, where scientists sculpt matter at the nanoscale to mimic the universe's most extreme phenomena. These lab-grown structures don't just imitate cosmic effects, they recreate them, offering a window into physics that would otherwise require interstellar travel to observe. At their core, vacuum metamaterials are built from arrays of microscopic resonators, each smaller than a wavelength of light. By carefully designing their shape and arrangement, researchers can force light to behave in ways that defy nature's usual rules. Take the invisibility cloak, a metamaterial that bends light around an object like water flowing around a rock, rendering it undetectable. The principle echoes how gravity bends starlight around a black hole, except here, it's not space-time curving, but the careful choreography of tiny metal loops and spirals etched onto a silicon chip. But the real magic happens when these materials simulate conditions even more exotic. One team created a black hole analog by stacking concentric rings of resonant structures. Light entering this artificial event horizon slows to a crawl, its energy siphoned away as heat, mirroring how real black holes trap photons forever. Another experiment engineered a material with negative refractive index, making light bend backward as if space itself had flipped inside out. Push further, and you could construct a tiny wormhole in the lab, not by warping space-time but by guiding waves through a metamaterial's labyrinthine channels, creating the illusion of a shortcut through dimensions. The implications go beyond cosmic mimicry. Metamaterials could revolutionize telecommunications, bending radio waves around obstacles or focusing light into beams thinner than a human hair. They might even unlock new energy technologies, like coatings that absorb sunlight from every angle or surfaces that radiate heat directly into space. Yet the most profound application lies in fundamental physics. By recreating black hole thermodynamics or cosmic inflation in a tabletop experiment, scientists can test theories about Hawking radiation or the birth of universes without waiting for a telescope to spot distant anomalies. Of course, these engineered cosmos have limits. A lab-made black hole won't crush you into a singularity, and a metamaterial wormhole can't transport matter-only waves. But that's precisely what makes them so powerful. They distill the universe's wildest behaviors into safe, controllable experiments. Every time light bends unnaturally or vanishes into a microscopic vortex, it whispers a secret about how gravity, quantum mechanics, and spacetime might intertwine on scales both grand and infinitesimal. The next time you hear about a black hole's gravity or a wormhole's curves, remember, somewhere in a lab, scientists are stitching together atoms to make those cosmic mysteries tangible. It's a reminder that sometimes, to unlock the universe's greatest secrets, you don't need a rocket, just a nanoscale blueprint and a dash of ingenuity. Quantum mechanics tells us reality is a swirling cloud of possibilities until suddenly it isn't. Your coffee cup sits definitively on the table, not in a fuzzy superposition of spilled and unspilled states. This transition from quantum weirdness to classical certainty isn't just about observation, it's about survival. Welcome to quantum Darwinism, a radical idea suggesting that the universe isn't just random at its core, it's selective. The stable, objective world we perceive emerges because certain quantum states are better at replicating themselves across the environment, imprinting their information on everything they touch while fragile states fade into oblivion. Think of it like a cosmic game of telephone. When a quantum system, say, an electron in a superposition of two positions, interacts with its surroundings, air molecules, photons, even the fabric of space-time, countless tiny observers in the environment record snippets of its state. But here's the twist: not all quantum states leave equal traces. Some are robust, broadcasting their information far and wide like a viral meme. Others are delicate, their signals crumbling under the noise of reality. Over time, only the most durable states persist, stamped into the environment so thoroughly that any observer, whether a human, a camera, or a dust particle, will pick up the same consistent message. This is how subjective probability collapses into shared fact, not because consciousness magically determines reality, but because the universe naturally amplifies certain truths while silencing others. The elegance of this process lies in its universality. Consider Schrödinger's famous cat, simultaneously alive and dead in its box. Quantum Darwinism explains why, when you peer inside, you never find a blurred, half-dead kitten. The cat's quantum states have interacted with thousands of air molecules, photons, and the box's walls long before you looked. These interactions act like an evolutionary pressure, where only states corresponding to fully alive or fully dead can propagate their information reliably. Superpositions that might have existed fleetingly get selected against, their fragile quantum coherence shattered by the environment's constant prying. What remains is a classical outcome, a winner in the Darwinian struggle for quantum persistence. This isn't just philosophy. Experiments with entangled photons and quantum dots have shown how environmental interactions distill specific states while erasing others. In one groundbreaking study, researchers watched as quantum systems entangled with their surroundings gradually leaked information about their state into the environment, but only for certain configurations. It's as if the universe has a preference for stories that can be told consistently, filtering out the narrative threads too tangled to survive. Even the act of measuring a particle's position isn't fundamentally different from a rock recording the shadow of a tree. Both are interactions where robust information proliferates while noise cancels out. The implications ripple far beyond quantum labs. If quantum Darwinism holds, it suggests that reality as we know it isn't the only possible version, just the most persistent one. Alternate histories and parallel worlds might flicker briefly at the quantum scale, but unless they can imprint themselves on their surroundings, they vanish like whispers in a storm. This could explain why we experience time's arrow moving forward. Irreversible environmental interactions constantly prune the tree of possibilities, leaving only the sturdiest branches to grow. Critics argue that the theory merely reframes the measurement problem rather than solving it, but its power lies in shifting the question from how observers collapse wave functions to which states deserve to be called real. In this light, objectivity isn't a given, it's an achievement, forged through countless quantum interactions that act as nature's editors. The chair you're sitting on feels solid, not because it's immune to quantum uncertainty, but because its atoms have spent eons convincing the universe of their persistence. Every time you touch, see, or measure anything, you're not creating reality. You're joining a chorus of environmental witnesses, all humming the same tune evolution has deemed worth remembering. Neutrinos are the ultimate cosmic shape-shifters, slipping between identities like quantum chameleons in mid-flight. Unlike protons or electrons, which stubbornly maintain their properties across the universe, these ghostly particles exist in a constant state of flux. An electron neutrino born in the Sun's fiery core might transform into a muon neutrino by the time it reaches Earth, then flicker into a tau neutrino before hitting a detector. This bizarre metamorphosis, called neutrino oscillation, isn't just a quirk, it's a smoking gun, proving that neutrinos have mass when the standard model long insisted they should be weightless. The mechanics behind this transformation are stranger than fiction. Neutrinos come in three flavors: electron, muon, and tau, each associated with their charged counterparts. But here's the twist: these flavors aren't fixed identities. They're quantum superpositions of three different mass states, constantly interfering with one another as the neutrino travels. Picture a musician playing three notes simultaneously, where the dominant sound shifts depending on how far the listener stands. For neutrinos, the notes are mass states, and the distance is governed by quantum phase differences that evolve over time. The result, a particle that's never quite itself, always cycling through probabilities of being something else. This behavior was first glimpsed in the late 20th century through the solar neutrino problem. Experiments designed to catch electron neutrinos streaming from the sun kept coming up short, detecting only a third of the predicted number. The solution: those missing neutrinos hadn't vanished, they'd changed costumes, oscillating into flavors the detectors couldn't see. Subsequent experiments like Super Kamiok and SNO clinched the discovery, catching neutrinos in the act of transformation by comparing counts at different distances. The farther detectors were placed from neutrino sources, whether the sun, nuclear reactors, or particle accelerators, the more dramatic the flavor shifts became, like a magician's trick revealed in slow motion. But the implications stretch far beyond particle physics. Neutrino oscillations imply that the Standard Model, our most successful framework for matter, is incomplete. If neutrinos have mass, however slight, there must be undiscovered physics explaining how they acquired it, possibly involving a right-handed neutrino, a seesaw mechanism with ultra-heavy partners, or even connections to dark matter. Some theories speculate that neutrino oscillations could be a window into extra dimensions, with the particles briefly leaking into hidden realms that alter their behavior. Others suggest these oscillations might have played a critical role in the early universe, tipping the balance between matter and antimatter to create the cosmos we know. What makes neutrino oscillations so revolutionary isn't just their defiance of expectations, it's their sheer ubiquity. Right now, trillions of solar neutrinos are passing through your body, oscillating silently as they traverse Earth's mantle, with flavors flickering like candle flames in a cosmic breeze. Future experiments like Dune and Hyper-K aim to exploit these oscillations, using ultra-precise detectors to probe mysteries from CP violation, a potential key to matter's dominance, to the possible existence of a sterile neutrino, a fourth flavor even more elusive than the others. Every oscillation is a whisper from the quantum underworld, reminding us that even the most elusive particles can't hide their secrets forever. The universe, it seems, loves a good costume change, and neutrinos are its most audacious performers. Science thrives at the edge of the unknown, and these 30 theories, they're the bleeding frontier, wild, untamed ideas redefining reality's rulebook. From dark matter's cosmic puppetry to holographic universes encoded on distant horizons, each one shatters assumptions we didn't even realize were holding us back. Think about it, we've mapped black holes bending starlight, yet we're still debating whether gravity is a fundamental force or just an illusion woven from quantum threads. We've measured neutrinos flickering between identities mid-flight, while parallel universes and fifth forces lurk in the math, waiting for their moment. What ties them together isn't just their strangeness, it's their audacity to question everything. String theory dares to rewrite particles as vibrating loops in hidden dimensions. The false vacuum whispers that empty space could annihilate us all in an instant. Even time itself gets upended by crystals that pulse forever without energy, defying entropy's iron grip. These aren't just thought experiments, they're battle plans for scientific revolutions, each one a potential key to unlocking the cosmos' deepest riddles. But here's the real magic. Some of these ideas are crossing from speculation into testable reality. The next decade could see a lab-grown black hole analog revealing secrets of Hawking radiation, or a neutrino detector catching whiffs of sterile particles from the dark sector. Maybe we'll spot a cosmic string's gravitational wake in telescope data, or simulate a baby universe in a quantum computer. The line between fringe and fact has never been blurrier or more exhilarating. So which theory grabs you? Are you team hologram, convinced reality's just a 2D projection? Or do you bet on white holes, those mythical cosmic fountains waiting to be discovered? Drop your favorite in the comments. Let's geek out over which mind bender might crack first. And if you're hungry for more cosmic curveballs, hit subscribe. The universe isn't done surprising us, and neither are we. Every answer breeds new questions, and the next revelation, it's already out there, lurking in the data, the math, or some lab's glow-in-the-dark detector. Stay curious, the wildest chapters of physics are still being